Yeah, thank you. A very good evening, everyone. Hearty welcome to the day 4 of our ATAL Faculty Development Program. It's been a wonderful journey so far with enlightening sessions, inspiring discussions, and valuable knowledge sharing. We are delighted to have all of you with us today as we continue this learning experience. Today, day 4 promises to be equally insightful. We have sessions lined up to be delivered by our distinguished speakers. I'm sure these sessions will broaden our horizons and inspire us to explore further. Now it's my privilege to introduce our esteemed resource person for the first session of the day, Dr. Ekta Goyal Madam. Dr. Ekta Goyal Madam received her BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lucknow in 2009. She completed her MTech and PhD in Microelectronics Engineering from IIT Bhubaneswar, Varanasi in 2013 and 18. Her area of research includes modeling and simulation of advanced nanoscale MOS devices, VLSI circuit simulation, photodiodes, and photovoltaic cells. Currently, she is supervising 6 PhD candidates. She has published more than 50 research articles, 5 book chapters in peer reviewed journals and conferences. She is working as an assistant professor in NIT Warangal. Prior to that, she has worked in JP Institute of Information Technology, Noida. She has been awarded Bharat Vikas Award for Outstanding Research by Institute of Self-Reliance Bhubaneswar, Odisha in 2019. She is a faculty advisor for IEEE Electronic Devices Society, SBC NIT Warangal. She is a senior member of IEEE, member of IEEE Circuits and Systems Society, member of IEEE Photonics Society, life member of Institute of Engineers, India. So without any further ado, I now hand over the session to our respected speaker. Over to you, ma'am.
So, topic of my talk is nanoscale semiconductor devices, low power and biomedical applications. So, starting with the evolution of electronic devices. So, before the invention of BJT, bipolar junction transistor, we were using vacuum tubes. So, vacuum tubes were very spacious, bulky. So, after the invention of BJT, we started using BJT, bipolar junction transistor. It replaced vacuum tubes. But at that time, the BJT was used as discrete component. So, when the integrated circuits were invented, when we were able to fabricate multiple number of transistors on same wafer, ICs we were able to fabricate. So these ICs replace the separate or discrete components. And in ICs fabrication, there are different scales. Small scale integration, when a maximum of 10 transistors, that time we were able to fabricate on the single wafer, single IC. Then medium scale integration, around 500 transistors we were able to fabricate. Then LSI, around thousands in thousands, and VLSI in millions of the transistors we were able to fabricate. And nowadays we are following this trend, VLSI. First point is how we are able to fabricate more and more number of transistors, and what is the advantage. So how we are able, because the fabrication uh, technologies, the technologies are getting improved day by day, new technologies are coming. So because of that, we are able to reduce the dimension of the transistor, dimension of the BJT. Actually nowadays MOSFET is used, advanced MOSFETs are used. So because of that, more number of transistors, more number of MOSFETs we are able to fabricate on the same size wafer, semiconductor device or ICs. But the thing is, what is the advantage? Advantages of this. So this miniaturization of MOS device dimensions is called scaling. And in 1965 and then again in 1975, scientist Moore, J.D. Moore, he gave one law on prediction basis, like every 2 years, number of transistors will get doubled in the ICs. And how? Because of this miniaturization. But what are the advantages of this scaling? Why we are moving towards this scaling? Because of this scaling, we are able to fabricate more number of transistors. Now, if we see any circuit, digital or analog, these MOSFETs are the basic component of any IC, of any circuit. More number of MOSFETs, more number of transistors means more number of sub circuits we are able to make in particular IC, or we can say a single IC can work for different circuits, or it can perform multitask. So because of this, it can accomplish, there is ability in the IC to accomplish multiple tasks simultaneously, same IC for multiple tasks. Cost is reduced. Why? Because it is the mass production in the same slot. All the transistors are fabricated. So cost is same, but if we see cost per function, it is reduced and speed is increased of the device. But there are some challenges, some limits in this scaling, in this miniaturization, and those are called mainly short channel effects, as the name suggests, short channel. So in MOSFET, we know there are different reasons like source, drain, channel, gate. So when scaling is done, so all the dimensions are reduced in some proportion. There are some guidelines, uh, and according to those guidelines, as per those rules, the device dimensions are reduced. It's not random. Randomly, we cannot reduce any dimension to any extent. Some guidelines are given. Following those guidelines, the dimensions are reduced, and all the dimensions are reduced according to some uh, factor. So short channel, as the name suggests, when channel of the MOSFET is channel dimension is reduced, then some effects are occurring, and those are called short channel effects. And these effects are basically going to affect the device performance adversely. So we have to get the advantages of scaling. We have to scale the device, but somehow we have to find some solutions, some remedies, so that these short channel effects can be reduced. High electric field effects, heat dissipation, power crisis. So all these we'll see. Coming to short channel effects, there are different short channel effects, but some important short channel effects regarding MOSFETs I am going to discuss here, like threshold voltage roll off. So if we see this graph, on y-axis threshold voltage is there, and x-axis we have taken channel length. So we can see for long channel length, this threshold voltage is constant, it is uniform. But beyond certain length, when length is reduced, channel length, then threshold voltage is not uniform, it is basically decreasing. But for ideal device, this threshold voltage should be uniform only, it should be constant irrespective of the channel length. But for practical devices, it will be reducing. So this reduction is basically threshold voltage roll off. Threshold voltage roll off is the difference between the threshold voltage at longer channel length and threshold voltage at shorter channel length. So the difference is called threshold voltage roll off. For ideal devices, it should be zero. In practical devices, this parameter is there present. Drain induced barrier lowering. Again, some barrier is reduced, and because of that, threshold voltage will be reduced in the device, and reason is drain voltage. So if we see the long channel device, this energy potential, the potential energy for long channel device. So for long channel device, when we are applying VDS voltage, it is constant. But in short channel device, the this barrier, basically this energy, it is reduced. Why? Because when some voltage is applied at the drain side, then what happens in MOSFET, when some voltage is applied at the drain side, then what happens, basically some portion of the channel is governed by this voltage, while in the ideal device, the entire channel should be governed by gate voltage. Gate voltage is a controlling voltage. But in practical device, if it is a short channel device, then this voltage, drain voltage, is going to govern some portion of the channel, and that is why the portion of the channel governed by this gate is reduced, and because of that, threshold voltage is reduced. So this is drain induced barrier lowering. Now similarly, punch through, if we see, so source, drain, and these are depletion regions. So for long channel device, these depletion regions are not going to touch each other. But in short channel devices, when we are applying some voltages, gate voltage, drain voltage, then at some voltages these depletion regions are going to touch each other, and when depletion region will be touching, then there is no meaning of the channel, there is no channel. Then how the device is going to work? This phenomena is called as punch through. Threshold, sub-threshold power crisis. So first we should understand what is this sub-threshold. So in MOSFET, there is threshold region, sub-threshold region. So threshold region is when proper gate voltage is applied so that there is a proper conduction of the current in the device, in the channel, then that is called threshold voltage. And the threshold reason is when gate voltage is more than threshold voltage, more than or equal to threshold voltage. When applied gate voltage is slightly smaller than the threshold voltage, then ideally the device should not conduct, no current should flow. But in practical device, that time also when applied gate voltage is slightly smaller than threshold voltage, some current starts flowing, and this current is called as subthreshold current. This region is called as subthreshold region, and the power dissipated because of this current is called as power, subthreshold power dissipation. So here if we see, when gate length or channel length is reduced, when reducing, then active power dissipated is increasing, and subthreshold power also is it is increasing, and at certain point in the gate length or channel length, when again we are reducing the gate length or channel length, then subthreshold power dissipation is going to be more than active power dissipation, and this is called subthreshold power crisis. Now we have to see what can be some possible solutions, some approaches, so that these short channel effects can be reduced. So there are different engineering, like structural engineering. Structural engineering means when we are applying some engineering in the structure of the device itself, when structure is modified, because of that, maybe even current conduction phenomena is changed, it is modified. So those engineerings come under structural engineering, like non-conventional MOSFET, novel devices, new MOSFETs, junctionless, for example, junctionless tunnel FET, FinFET device, or vertical devices. Another approach is gate engineering. Means when we are applying some engineering, some technique in the gate region of the device, like multi-gate structures, when more than one gates are used, or gate material we are changing, or a combination of gate material is used, or gate oxide, when gate oxide is we are changing the gate oxide, or the pattern in which the gate oxide is used, the pattern is changed. So those all engineering will come under gate engineering. Similarly, channel engineering, if we are going to apply some engineering in the channel region, like doping profile we can change, or material in the channel we can change, or we can induce strain in the channel, and some other engineering if we are applying in the channel, that will come under channel engineering. Similarly, source drain, if some engineering we are applying in the source drain region, like heterostructures, different materials we are using, elevated structures, doping profiles we are changing, those will come under source drain engineering. So some multi-gate structures we'll see, like this is double gate structure. So this is source, this is drain, this is channel region, and this is the gate oxide, red color, and blue is gate contact, gate material. And similarly at the back side, so top and bottom, this is called top gate, this is called bottom gate. Two gates are there. Now why we are increasing gate number of gates, and what will be the advantage of increasing number of gates? Basically, the basic reason behind short channel effect is when gate starts losing its control over the channel, then these short channel effects start occurring, like DIBL we have seen. So when drain is controlling some portion of the channel, and the portion of the channel controlled by the gate is reduced, then this DIBL will occur. Similarly, other effects also. So somehow we have to increase the gate control over the channel. So what we can do here, we have taken gate from two gates, one from the top side, another one from bottom side. So this channel is covered from both the sides, and because both the sides gate are covering, so this control of the gate is going to increase. Similarly, here we can see tri-gate. So gate is covering the channel from three sides. Similarly, quadruple gate structure can be there, and cylindrical. This is in the form of cylindrical only, cylindrical shape. So this is source, this is drain. In between there is channel which is covered by oxide, and then gate. So these are some multi-gate structures. Now coming to this one structure that I am going to discuss, it is graded channel dual material double gate MOSFET. So if we see the MOSFET, this is source region, drain region, this is channel region. Now this is top side of the gate, top gate, and this is bottom. So because of this top and bottom, because two gates are used, so it is called double gate. Now coming to dual material. So dual material means we can see this gate here. Phi m1 is written here, phi m2. Phi m1 is nothing but the work function of the material that we are using for the gate in this portion, in this half portion, and in the remaining portion, we are using some other material having work function phi m2. So two different materials we are using in the gate. That is why it is called dual material. And another thing is, I have taken here symmetric device. Symmetric means whatever dimensions, materials, combinations that we are taking for this front gate or top gate, the same parameters we are taking for this bottom gate. So this is dual material double gate. Now coming to graded channel. So if we see the channel, so we have this divided the channel into two regions, region 1, region 2. In region 1, the doping is Na1, acceptor doping, p-type, it is Na1, which is uniform, which is constant. It means at any point in region 1, doping is Na1. And similarly, another region Na2, where doping is Na2, it is again uniform, constant. So now to analyze any device, this MOSFET is basically the very basic building block of any IC. And in nowadays, if we see in any area, whether it is your day-to-day life or medical or military applications or any field, we can see IC, electronic gadgets are used. And the very important, or we can say the building block of any electronic gadget is IC, integrated circuit. And very basic component of any IC is this MOSFET. So we are working on this MOSFET. We are trying to improve the performance of this MOSFET, which ultimately is going to be reflected in the performance of IC and then again in the performance of electronic gadget. So if we see here, this device, now we have to analyze this device for a short channel device, for short channel length, and for low power application. So there are three methods to study a device. One is the experimental study, another one is the simulation, and third one is mathematical modeling. So first, coming to experimental study means in real time we are taking this wafer, then we are fabricating this device, then we will characterize, we'll see its performance, we'll measure its parameters, and then again if the device is not working properly, again we are going to fabricate the device, and then again we will characterize, again we'll see if it is not working, we'll do some modifications, and like this. So whenever we are going to fabricate the device in the real time, it will take much time. Time is required, energy is required, and money is required for this fabrication. And the main point is, in fact, this fabrication facility at this very at this scale, like sub 5 nanometer technology node, sub 10 nanometer, sub 7 nanometer, it is not available still in India. So if we are going at that small level technology node, then we have to get the device fabricated from some other country. So this is related with these nanoscale devices. And now coming to another study, another option like mathematical and simulation. So mathematical is like we'll take the basic equations and we'll apply some boundary conditions as per the device, as per the specifications of our device, and then we'll apply the mathematical formula, we'll formulate it, and we'll develop some models for the parameters of the device like threshold voltage or current on, current off, current, all that. So this is another way. And third method is simulation. In simulation, we'll be having some simulation software, and virtually in that software we'll make the device, will apply all these specifications, the like this will be the source length, this is channel length or drain length, and what will be the doping, what will be thickness, or which material we are using, then material properties, everything, and more importantly which model we are going to use. So in every simulator, there will be some model to include. So some models like mobility models and different models are there that we'll be using depending on the device, and then we'll see the performance of the device. When run simulation, we'll see the performance. So here for this device, I'm going to discuss first how mathematical modeling can be done. So because it is a 2D, two-dimensional device. this is two-dimensional device. So we have taken 2D Poisson's equation. This is two-dimensional Poisson's equation. And then we have to apply some condition again to solve, to find out like surface potential, channel potential, then threshold voltage, current, all those formulas, all those expression. So there are different methods like parabolic approximation method, or Evensen mode analysis method, or some charge based method modeling. So here I'm taking this parabolic approximation function. So here the channel potential, we are assuming it is a parabolic function, and then after that we are applying some conditions, so boundary conditions. So these boundary conditions are nothing but like at these interfaces here, the potential and the flux are electric field and electric flux that are continuous. Suppose if we take this interface, so whether we calculate from region 1 or whether we calculate from region 2, it is same only. So same boundary conditions like uh, surface potential at L1 when we are calculating from region 1, and surface potential again at L1 when we are calculating from region 2, they are equal. And similarly here if we see at L1 only this uh, flux is same. Now coming to again surface potential at 0. 0 means here we have taken origin. So here this is x is equal to 0 and this x is equal to L, and this is y is equal to 0 and this is y is equal to TSI, thickness. So for x is equal to 0, if we see this is n plus source and this is p plus region, p type region, basically PN junction. So built-in voltage is going to be present here. So same thing we have written at L is equal to 0, the potential will be equal to the VBI, built-in voltage. 1 means for region 1. And similarly, when we go at here at L, so it will be VBI2, which is built-in voltage at region 2 plus VDS. VDS is nothing but drain voltage, drain to source voltage. So similarly, then after that, by applying these boundary conditions, just simple math, and we have formulated the channel potential or surface potential. Now coming to threshold voltage. So again, threshold voltage, depending on the device conduction, current conduction phenomena, different definitions can be used. For our device, it is like the threshold voltage is the gate voltage where minimum of surface potential is equal to twice of Fermi potential. So this we have used, and then after that threshold voltage is formulated. Then after this the results are drawn. So we have done simulation as well as we have done mathematical modeling. So both the results, line is basically mathematical modeling results and symbols are basically simulation results. So we have drawn, we can see like they are overlapping, the line and symbols. So it shows like our model is correct and our simulation is also correct. Both are matching. Okay. Now coming to the results and discussion part. So here we have taken three devices. One is GC-DMDG. It is graded channel dual material double gate. Then next is dual material double gate, and next is graded channel double gate. So graded channel dual material double gate is the structure that I have explained, I have taken. Now DMDG is dual material double gate, where graded channel we have not taken. So instead of graded channel, in entire channel only one doping concentration is used, and the doping concentration is average of Na1 and Na2 for proper comparison. And similarly GCDG, graded channel double gate. So graded channel is there, double gate is there, but dual material is not present. So instead of dual material, we have taken single material in the gate, and the work function of that material we have taken the average of phi m1 and phi m2 for proper comparison. So what we see here among the three devices, when we are applying both engineering, graded channel as well as dual material, the red color graph, so minima of surface potential is minimum among the three. So surface potential minimum means barrier is maximum, and barrier maximum means threshold voltage will be maximum. Maximum means we can say the deviation in the threshold voltage from long channel device, long channel value will be small. A threshold voltage roll-off will be small. So that we'll see in the coming slides also. So again, here surface potential is drawn for different values of this ratio L1 by L2. So if we see this L1 by L2, so total length is L, where L1 is where phi M1 is used and Na1 we have taken, and phi M2, the L2 is the remaining portion where phi M2 is used in gate and Na2 is used in channel. So here what we see, when this ratio is like 1:2, this red color graph, and when we are increasing the ratio to 1:1 and 2:1, then when we are increasing this ratio, minimum surface potential is minimized. So again, when minimum surface potential is minimized, barrier will be increased, threshold voltage will be increased at shorter channel length, small channel length, or we can say the deviation in the threshold voltage will get reduced, and deviation is nothing but threshold voltage roll off. It is a short channel effect. Now, when we draw the threshold voltage for the three device, so again we can see, like when we see the long channel device, so at long channel device, if we see the red color and green color, red color means the GC DMDG and green color DMDG. So at long channel device, there is not much difference, but when we come to short channel, so this difference is more. Or we can say, if we find the difference of threshold voltage for a particular device, say GC-DMDG. So difference means the threshold voltage at longer channel length minus threshold voltage at smaller channel length. So this difference is nothing but threshold voltage roll off, and this roll off we are going to get minimized value for this case, GC-DMDG. So what we see here among the three devices, GC-DMDG is giving better results in terms of reduced short channel effects. Threshold voltage for different values, this L1 by L2. So when L1 by L2 is increasing here, like this maximum value we have taken 2:1, which is blue color graph, and the minimum value 1:2, red color graph. So for long channel device, they are almost comparable, but shorter channel, for short channel device at shorter length, channel length, when this ratio is increasing, then threshold voltage is increasing. Again, if we see the difference between long channel and short channel device, so this blue color graph, for this blue color graph, we are going to get minimized value. So threshold voltage roll off will be minimum for 2:1, maximum value of L1 by L2. Now this result is very important result, like threshold voltage versus device channel length for different values of VDS. So VDS means drain to source voltage. So here we can see when VDS value we are applying 0.1, though then we are getting this blue color graph, and when we are increasing, then we can see at longer channel length there is no difference, but at shorter channel length, when VDS value is increasing, threshold voltage is decreasing. So this result is basically showing the IBL effect. When drain induced barrier lower, when drain voltage is increasing, barrier is decreasing. Barrier decreasing means threshold voltage is reducing for shorter channel device. For long channel device, it is same. So this is the effect of VDS. And similarly, we can see the effect of doping concentration like Na1. So if we see the green color and blue color, green color, so TSI thickness is 10 nanometer, for blue color also TSI 10 nanometer, and other parameters are, these values are given. But Na1 means doping in the region 1, we are changing. So for blue color it is 1 in 10 power 17, for green color 5 in 10 power 17. So when doping is increasing, what we are observing, threshold voltage is increasing. And similarly, if we see green and this violet color graph, so doping is same, TSI is changing. So for green color, TSI 10 nanometer, for violet color, TSI 12 nanometer. So when TSI is increasing, what we are observing, for long channel device, there is no change in threshold voltage. But for short channel device, when TSI increasing, then threshold voltage is decreasing, because length is same and thickness we are increasing. So somewhat device is basically approaching towards short channel device, because thickness we are increasing, channel length is same. So this ratio L by TSI, length by thickness, it is reduced. So we can say device is approaching towards short channel device and short channel effect is occurring. So this is another important result. Here we see the threshold voltage roll off for three devices for different control gate length. Control gate length means this L1. So, and again, DIBL we have drawn for this L1. So we are changing only L1. L is same. L we have taken 30 nanometers. So L is 30. L1 we are changing. Say L1 we are taking 10. In that case, L2 will be 20, because L1 plus L2 is L. And suppose L1 is 20, then that time L2 will be 10. So what we are observing, like among the three, GCDG, GCDMDG, DMDG, and GCDG. Threshold voltage roll-off is minimum. This is minimum for GCDMDG, red color graph. It is minimum. It means among the three, GCDMDG is giving best result in terms of minimized threshold voltage roll-off. And another point that we observe here, like when we are increasing this L1 control gate length, then for all the device, whether it is GCDG, DMDG or GCDMDG, threshold voltage roll-off is reducing. It means increasing L1 is giving better results in terms of reduced threshold voltage roll-off. One point. While coming to another parameter, DIBL. So again, among the three, we can see this DIBL is minimized for GCDMDG. Again, showing among the three structures, GCDMDG will be giving the best results in terms of smallest DIBL value. But another thing that we observe here is when we are increasing control gate length, then this DIBL for all the device, it is increasing. It means same parameter, same variation is giving desirable result in terms of one parameter and adverse result in terms of other parameter. So this is called trade-off. So we have to select this value L1 or L2 or L1 by L2 such that both the short channel effects, threshold voltage roll-off and DIBL, they should be in tolerable range. As per the application, we have to see. Okay. Similarly, when we draw the sub-threshold current is when the applied gate voltage is smaller than threshold voltage. In that case, the current which is flowing, that is sub-threshold current. So it is considered as leakage current, and ideally it must be zero. But in practical devices, some value is there, so which we are trying to minimize this value. So we see here among the three devices, GC-DMDG, DMDG, and GCDG. So this blue color is GC-DMDG. So sub-threshold current is minimum for GC-DMDG, again showing the superiority of this structure when both engineerings are applied, GC and DM. Similarly, when channel length is increased, like channel length 40 means this blue color, and when we are increasing, so we can see sub-threshold current is reducing for all gate voltages, it is reducing. Obviously, when channel length will increase, means device is moving towards long channel device. And in long channel device, these effects, short channel effects are automatically, they will disappear. So that is why sub-threshold current is reducing when we are increasing the length. When we are increasing this ratio, so we can see for 2:1, meaning increased value of this ratio L1 by L2, current is decreased. Already we have seen sub-threshold, this threshold voltage roll-off will be decreased. So another parameter is sub-threshold swing. So sub-threshold swing, this parameter is basically going to decide the switching performance of the device, of the MOSFET. Switching performance means when we are using this MOSFET as a switch in digital circuits, so to move from on to off or off to on, the switching time should be as small as possible so that switching will be fast. And this switching will be decided by this parameter, sub-threshold swing. So for conventional devices, for normal MOSFETs, this value, the minimum value of sub-threshold swing is basically 60 millivolt per decade. And or otherwise it will be more than 60 millivolt per decade. But the desirable value is as small as possible. A smaller value of sub-threshold swing signifies better switching. So here we see for the three device, like for long channel, like when we are moving, means more than channel length is more than 40 nanometer, then it is almost same and almost approaching towards the 60 millivolt per decade value. But when channel length is less than 40, 35 like that, then sub-threshold swing is increasing for all the device. But among all these three devices, sub-threshold swing is again minimum for GC-DM-DG. So again showing the superiority of this structure, benefit of this structure. Similarly, this ratio, effect of this ratio, we can see when we are increasing this parameter L1 by L2, sub-threshold swing is decreasing. Okay, so this was one structure that I have discussed here. So what we have seen here basically, so we have taken some structure, double gate MOSFET, some structure, and then we are applying some engineering, some channel engineering, gate engineering I have applied. And after that, we are observing the effect of variation in the device geometrical parameters or doping parameters like L1, L2, L1 by L2 or phi M1, phi M2, all those parameters we have seen how they are going to affect the device performance. Device performance like sub-threshold current or surface potential, threshold voltage, DC parameter, and so we are going to see how they are going to affect. Or we can say when we know what parameter is going to affect our device performance in which way, then we can tune the device performance, we can tune that parameter, we can fix value of that parameter so that for a particular application our device is perfect. So similarly, moving to some other device, this is ion implanted stained silicon double gate MOSFET, dual material double gate MOSFET. So what we see here, like MOSFET is clear, double gate, top gate, bottom gate. So again, I am taking symmetric device. Whatever parameters are there for top gate, same parameters we have taken for bottom gate. However, we can make the device asymmetric also, and accordingly, the device performance will be modified. Now, dual material. So two materials we have taken for gate having their function phi M1, phi M2. Now coming to ion implanted and stained silicon. So ion implanted is nothing but actually in the previous case we have taken uniform doping. But normally when we fabricate the device in real time, so that doping profile is found the Gaussian doping profile, and this is called ion implantation, ion implanted. Through ion implantation also we normally get Gaussian doping profile. So ion implanted is nothing but that Gaussian profile we are going to take in the channel. It is not the uniform. Another one is strained silicon. So this strained silicon is in the channel region we are going to create some strain. So because of that strain, basically the silicon atoms will get stressed and there will be clear path available for the carriers, for the electrons to move from source to drain, and because of that speed of the device is going to increase. So this is the reason behind considering strained silicon. There are different types of strain and there are different methods how to create the strain in the channel. So that I'm not going to in depth of that. And now coming to the effect of strain. So by some researchers already it is reported in the literature, like this is germanium mole fraction X. So one method of creating strain is, suppose we are having silicon wafer. So if we grow germanium layer over some silicon layer, then because interatomic spacing of germanium atom is more than the interatomic spacing of silicon atoms. So to match this interatomic spacing, once the germanium layer is grown over silicon, then silicon atoms try to match this interatomic spacing with the germanium atoms, and because of that silicon atoms got stressed. And the main point is it is reported, it is found in experimentally, like after this if we remove germanium layer, then also these silicon atoms remain strained only. So this X germanium mole fraction that we are writing, it is basically showing strain. More value of germanium mole fraction in that layer, it will create more strain. So and this effect mathematically it is already reported that we have taken how it is going to perform, how it is going to impact the our modeling, mathematical modeling. Now coming to Gaussian like function or Gaussian. So if we see here first, so Gaussian profile, this green color graph we have shown. Now coming to this red color, this is Gaussian like. This is Gaussian like basically. If this is the Gaussian, normal Gaussian function, so that we can take because we are working on doping, channel doping. So that is why we have written in terms of doping only. This is peak doping in the channel. This is the doping in the channel at any position of y, And this capital Y is nothing but small y. Y is the position, is small y, xy coordinate, and RP divided by YB. RP is nothing but the projected range, and sigma p is called the straggle. Straggle means the spread of the graph. So sigma more means this spread will be more, and sigma less means this graph will be narrower. Now, this is the Gaussian function. Now, when we model our device, mathematical modeling, when we do and we take this Gaussian function, so basically this function is not double integrable. It is not integrable twice, means it is not giving the converging result. Then in 1986, Das Gupta et al., they have proposed one another function which they called as Gaussian-like function. Here, some fitting parameters are there, A, B, C, and these are the values to fit this graph with the normal Gaussian graph. So these are the fitting parameters, and this function is called the Gaussian-like function. So because we are using in doping, so in terms of doping, we have used this. So this is the Gaussian-like. So this Gaussian-like function is basically integrable, and it will give the converging results. That is why this function is included in the doping. And similarly, as we have modeled the previous device, similar way we have modeled this device also, and then we have drawn some results. So like L1 by L2, same pattern, same result we are getting here also. With increasing value of L1 by L2, we are getting reducing value of subthreshold surface potential. Surface potential reduced means barrier increased. Barrier increased means threshold voltage at lower channel length is increased. And similarly, this doping, peak doping. So this peak doping means uh, this doping peak. So we can say, if we see the device, here we have taken origin. So maybe we are taking peak doping here. So it means maximum doping at this interface, and then from this interface to this interface at both the sides, doping will be reduced in Gaussian, like Gaussian function manner, in this pattern, Gaussian function. So this is the doping. When peak doping is increased, then the entire doping, or we can say the average doping in the channel, will increase, and that is why when peak doping is increasing, threshold voltage is increasing. And same we are getting here in this device also. But the thing that I would like to discuss here is this graph. So here we see RP 0 and RP minus 3. So what does it mean, RP? So RP0 means RP is basically, we can say it is value of Y. So I will just show here. RP0 means Y is equal to 0. So Y0 we have taken in the middle of the channel. So RP0 means peak doping we have considered where Y is 0. It means in the middle of the channel. And when we are writing, say if I say this thickness is TSSI, so where this will be TSSI by 2, and because origin is in middle, and this here it will be T minus TSSI by 2. So if I say RP is equal to TSSI by 2, it means at this interface we will be taking peak doping, and then doping will be reduced to the at this interface. It will be continuously reducing. So when doping, we are taking peak doping in the middle. In that case, the device will be symmetric, because whatever doping will be there in this at this interface, same doping after reduction it will come at this interface. And because all parameters are same, so whatever threshold voltage we will get for front gate, same threshold voltage we are going to get for back gate. Or because here also we are applying same voltage, VGS. So these are connected basically. So it means at the same time both the gates are getting on and current is flowing. So current is flowing in both sides, both gates, and that is why maximum current will be flowing. And now coming to another situation, like if I say peak doping we have taken at this interface. So when peak doping here, so according to this Gaussian, peak doping will be reduced, and here at this interface doping will be minimum. So because here doping is minimum, so threshold voltage will be minimum for this side gate, and threshold voltage will be maximum for this. But because same voltage is applied So suppose we are applying gate voltage initially 0 and then we are increasing slowly. So when we are increasing, then this gate will get turned on at some voltage. And once this gate is on, then this gate will never on. So this gate will be on, current will be flowing, device is working, but this gate will never on. So only half of the current we will be getting because only one side of the gate is working, another is not working. So purpose of double gate is lost. So what we are getting here, like if we take RP0 or if we take peak doping in the middle of the channel, that time both gates are on and we will be getting maximum current or maximum performance of the device. So this is, we can see here like RP0 means this blue color. So this is basically leakage current. This is leakage. This is not the on current. Subthreshold current is leakage. So here it is reduced. We are getting minimum leakage current. Why? Because threshold voltage is maximum. And when we are coming here at any other value, in that case, threshold voltage will be reduced. And because of that, subthreshold current will get increased. Leakage current will be increased. And when we'll come to on current will be reduced. This is the point here. So similarly, this L1 by L2, same we have find out on subthreshold swing. When L1 by L2 is increasing, subthreshold swing is decreasing. So higher value of L1 by L2 is desirable in terms of reduced value of subthreshold swing. Reduced value of subthreshold swing means faster switching. So similarly, doping, when we are increasing doping, peak doping we are increasing, so average doping or the entire doping in the channel will get increased. Subthreshold swing is reducing. Now coming to the conclusion. So what conclusion we are getting here? So the two devices we have taken here, we have seen in the two devices, we have used gate engineering and channel engineering, both the devices. So, but in the previous device, first device, the parameters that we are having in our hand that we can tune. So those are L1 by L2 or phi M1, TSI, channel length, these parameters. Now coming to second device. So in second device, parameters are same as the first device, L1 by L2 or phi, thickness, TSSI or channel length, all these parameters. But additionally, we are having some other parameters also like RP, we are having sigma P. So the additional parameter of this Gaussian like function, we are also having these doping parameters we are having in our hand that we can change, we can modify, we can tune to get the desired performance of the device. So this way basically what we have seen, like how we can optimize the device performance. So when we are doing simulation, by adjusting these parameters, we can see where we are getting maximum performance. Now coming to some other novel devices like tunnel FET. So the devices that we have seen up to now, those were MOSFETs. MOSFET current conduction was there. Now coming to tunnel FET, tunnel field effect transistor. So tunnel field effect transistor is nothing but gated pin diode. So pin diode, PIN. And if we use dielectric and we use gate, then it will be, so this will be working as tunnel diode. So what are the advantages or disadvantages? What is the difference basically? So in the normal MOSFET, basically current conduction phenomena is based on thermionic emission. Means carriers in the source have to overcome some barrier and then they will come, they will reach to drain. In tunnel FET, this phenomena is different. It is based on band-to-band tunneling. So these, hello, hello, shall I move?
Yes,
So,
ma'am.
okay. So here, the phenomena is band-to-band tunneling. So carriers will be tunneling through these bands and they will be moving towards drain. So this is the difference in current conduction phenomena. Now coming to some advantages or drawbacks. So in conventional MOSFET, on current is high as compared to tunnel FET. So this is advantage of MOSFET. Now coming to subthreshold swing. Subthreshold swing is basically, it is minimum value of, in MOSFET it is 60 millivolt per decade and we want even lower value. So in tunnel FET, we can get smaller than 60 millivolt per decade. So this is the advantage of tunnel FET. Now power issues. So power issues means for when we are reducing the dimension, we are getting power issues in MOSFET as well as this tunnel FET. But in tunnel FET, off current is very small, leakage current. So this is one of the advantage of tunnel FET. Off current is very small. SS is also, subthreshold swing is small, and drawback is on current is low. So we have to find some solution in tunnel FET so that on current can be increased. And another thing is ambipolarity. Now what is this ambipolarity actually? Ambipolarity means, suppose we are using these device in any circuit as a switch. Switch means in one direction current should flow, and in another direction means, suppose for if we see the MOSFET, we are using positive gate voltage, so it will be on, and when we are using negative gate voltage, the device will be off, there will be no current. But in tunnel FET, what happens? When we are using positive gate voltage, then current will be flowing in one direction. And when we change the polarity of this gate voltage, then current starts flowing in another direction. So suppose for positive gate voltage, this is working as source, this is working as drain. And if we change the gate voltage, polarity of the gate voltage, then this will start working as source, this will start working as drain, and in opposite direction current will flow. This is called ambipolarity. So if when ambipolarity is there, the device cannot be used as switch. So we have to reduce this ambipolarity. So the solution, we'll see how we can do this and how we can reduce. So some different variants or some different engineering we have applied in tunnel FET, and we have seen. So like this is double gate tunnel FET. So source, drain, this is reason, channel reason, then this is front side, this is back side. So this is double gate tunnel FET. But here if you see the gate oxide, so we have not taken a single gate oxide. There are different gate, means SiO2 as well as some high K material, maybe HFO2, ZrO2, some other insulator oxide. So why this stacked form is used? So basically when scaling is done, when dimensions are reduced, then all dimensions are reduced. So this thickness, gate oxide thickness is also reduced. When this thickness is reduced, in that case, what happens basically, some carriers start flowing in this direction. Why? Because this electric field will increase in this direction, vertical electric field will increase, and carriers will flow in this vertical direction also, which is not desirable. So that current is called basically gate tunneling current. In fact, in MOSFET also, whether it is MOSFET or tunnel FET, any device, this vertical flow is not supposed to be flow this current, but whenever this current flows, this is called gate tunneling current, and we have to reduce. So solution is, like, if we use some high K dielectric material, so the for the same value, for same field, this physical thickness will be more in high K dielectric. So there is a concept of EOT, again different concept. This EOT, equivalent oxide thickness. So the physical thickness is more. So physical thickness more means now electric field will get reduced for same capacitance. Electric field will get reduced and carriers will not flow in this direction. So that is why gate tunneling current will get reduced. Now, if this is the thing, then why we are using SiO2? So as we know, the basically whether it's MOSFET or tunnel FET, any device, basically this interface should be the channel and oxide. This interface should be of very good quality. Good quality means there should not be any defect or any trap charges. But when we are using directly some other material, HFO2, ZrO2, in contact with this silicon channel, then this interface quality degrades. At the time of fabrication, some unwanted charge will get trapped. Those are called trap charges. So the performance of the device will going to be changed, degraded. So that is why we'll use one very thin layer of SiO2 to maintain the quality of this interface. And then over that we can use high K material, so that to increase total physical thickness, so that electric field will get reduced and this carriers will not be flowing. This is the reason. Now, if we see the parameters that we have taken for this device, so the normal parameters we have taken, but one thing here to notice is, normally in MOSFET, when we see source doping and drain doping, they will be, normally we take equal and higher doping only. But in tunnel FET, whether it is planar double gate or a vertical device or any device, in tunnel FET, any paper you will see, Source doping will take higher value, and drain doping, it is higher value only, but it will be less than source. Why? Because if somehow gate voltage polarity is changed, then this will be working as source. And because it is doping is quite smaller than drain, so in that case, this will not be able to inject much carrier in the channel. So that is why this ambipolarity effect will be reduced. So one solution to reduce this ambipolarity is to reduce the drain doping than the source doping. Now, coming to the results, like when we are drawing this energy band diagrams for the device that I have discussed, this is an off state, this is on state. Off state means VGS voltage we have taken 0, on state means VGS voltage, some VGS voltage we have applied, for example 1 volt. So here what we see, the carriers basically have to tunnel from source side to drain side, from here valence to conduction of the drain, but this distance they have to cover. But this distance is quite long and carriers are not able to tunnel through this distance. But in the on state, bands come closer to each other. This distance is reduced and carriers easily can tunnel this distance and they can come towards drain side. Valence band in the drain and current conduction will start flowing. So this is the tunneling. And this volume where the carriers are tunneling, this is called tunneling volume. Now, coming to another variant, so it is dual material. So same structure, but here two materials we are using, and we'll see what is the effect of this dual material, whether we are getting any advantage or not. So this basically this portion of the gate is called as tunneling gate, and the remaining portion is called as auxiliary gate. So what we see here, basically we have taken three cases, like single material we are using, where material work function is 4.4 electron volt. Another result, another graph we have drawn for single material only in the gate, single material but having work function 4.2. And then we have taken another dual material having work function 4.2 and 4.6. So for 4.4, we can see green color graph. So this is basically on current, this one. And here, because here this is gate voltage 0, 0 means this is off current. And when gate voltage, negative gate voltage, polarity is changed. So here, whatever current will be, that will come under ambipolar current, ambipolarity. So we can see this green color graph. Now, when we are reducing this voltage, this value by phi value, work function, so on current is somewhat increased and ambipolar current is reduced. So this is advantage. But when we are taking this DMG 4.2 and 4.6, so then what we are observing, on current is increased, on current is like with same as red graph only, but the ambipolar current is again reduced. So we are getting the advantage in terms of reduced ambipolar current when we are using dual material structure here. So, and similarly, ion by IF ratio, again, we can see for DMG. So it is comparable with the SMG 4.2 only. But here we are getting advantage in terms of reduced ambipolar current. Now, how to optimize, how to how to take these values 4.2, 4.4, 4.6, all these. So we have to see, we have to optimize. So we have taken different values. Phi T means tunneling gate, this one, this one. So we have taken different values, 4, 4.2, 4.4, 4.6. And the another one, auxiliary, is 4.4, that we have fixed. So when we are changing this value, modifying, so for 4.4, this green color means on current is maximum. And then when we are reducing, on current is reducing, with reducing value of 5. But what we observe, or come to off current, gate voltage 0. So what we are observing, for the remaining three cases, gate voltage is off current is very, very small, 10 raised to power minus 16 ampere per micrometer. So among the four, we can see this blue will be the optimized value, because on current is also maximum, almost comparable to green, and off current is quite small. For green, it is even more than 10 power minus 12, but for remaining three, we are getting 10 power minus 16. And similarly, we can optimize this value also. So this is the way to optimize. This is the way to find like what is the impact of these parameters on our device performance, on the current, on other values. And in the similar way, we can optimize the device. Similarly, L2 by L3. L2 by L3. So here basically this length is L2 for M1, and for M2 this is L3. So previous device we have taken L1, L2, here L2, L3. So similarly we can optimize this ratio also. So what we can see here, for 3:2 maximum current, but off current is high. For 1:1 on current actually for all the cases it is almost comparable. But if we see the off current, so off current we are getting minimized value in case of 2:3 and 1:4. But again, if we see 2:3 and 1:4 means blue and red. So blue is giving more value of on current. So that is why we can say blue is max optimized. So 2:3 is optimized. So similarly, this is another variation. So here what we have changed, heterojunction. This is basically heterojunction. Heterojunction means the previous device that we have studied, those were made up of single material, that was silicon. But here this source we have taken of germanium material. Germanium material we have used to make this source. This is called heterojunction device. Now coming to another study that we can perform on this device, and we can analyze the device, how it will be impacted. It is like dual material. Dual material is there. Heterogeneous gate dielectric. Now what is this heterogeneous gate dielectric? So if you see here, high K and SiO2, two different dielectrics we have used, but in the previous device, the pattern was different. It was like in vertical direction. First SiO2 in the entire channel length, and then over that we were using high K. But now the pattern is in lateral direction. For some portion we are using high K, and for remaining portion we are using SiO2. So uh, now what study we have done, because we are using high K directly with silicon, so there will be some interface trap charges. So that is why in simulation intentionally we have included those charges to see the performance of the device. So that also we can do. Now coming to very what we say, the novel structure, it is negative capacitance source pocket double gate tunnel field effect transistor. So this is again tunnel field effect transistor, but new structure, new variant. So two engineering we have applied. One is source pocket, one is negative capacitance. So source pocket is basically PN kind of structure. So P plus source, N plus drain, this P type channel, and a pocket. Pocket means N plus doping is used here, and this is called pocket, source pocket. So PN, and negative capacitance is included, like in the gate oxide only. One thin layer of SiO2 is used, and then over that we are using some ferroelectric material, HZO, or some other material we can use. So this is the structure. Now what study we have done, first of all we have optimized this structure. Optimized means we have to see like what will be the thickness of this ferroelectric. We have to see where we are getting the best performance. So first of all, this is negative capacitance source pocket, blue color. Then another reason, another device that we have taken only source pocket, no negative capacitance. And third, we have taken only double gate, or we can say first we have taken double gate, normal double gate tunnel field effect transistor. Then we have included source pocket, and then we have included another engineering negative capacitance. So what we see here for the normal double gate, the black color graph. So the graphs are means the bands are not very close, but when source pocket is included, pink color. So graphs are coming closer to each other, bands are coming closer, and when we are including negative capacitance, then again bands are coming closer. Closer means this distance is reduced and tunneling will be more tunneling mean more on current will increase, and that we want in tunnel fed, because on current is small, so we have to increase the tunnel. So this is one solution. Now here we can see like on current, if we see blue color, negative capacitance source pocket, it is giving maximum on current. Now see one another very
Madam,
good.
sorry to interrupt, madam. Can I kindly request you to wrap the session in 5 minutes, ma'am, because we have one more session
Okay,
in
okay,
this.
okay, okay, fine.
Thank you.
Yes. Okay, so subthreshold swing, if we see, so for this device, we are getting minimized value in around 20 millivolt per decade. It is very much reduced. Now to optimization, if we see optimization, so ferroelectric thickness, we have taken different ferroelectric thickness and we observe this SS subthreshold swing, we are getting minimum value, and minimum value of subthreshold swing means better performance. And ion by I of ratio, we are observing maximum. So that is why we can say this is the optimized thickness, ferroelectric thickness. So this is the optimization. Now another is application of this device that we have seen is in biosensor. Biosensor is something which is going to sense some material, some biological component in some compound, in some substance. So like a biosensor is like what property we are using? It is dielectric constant, like biomolecule, air, gluten, genin, keratin, different biomolecules having different dielectric constants associated. So to make the biosensor, what we have done, this ferroelectric is etched and cavities are formed so that biomolecule will be injected. In simulation we have done, in practical device they will come, biomolecule in the presence of biomolecule, device will be kept, and that will observe the variation in device performance, like what will be the variation in current, what will be the variation in subthreshold swing, all that. And accordingly we will see. So these are some sensitivity parameters, like what will be the on current when biomolecule is present, and what will be the on off by off current ratio when biomolecule is not present, only air is present. These are the formula. So as per those formula we can calculate, and what we see, biomolecule can be neutrally charged or positive charge or negative charge. So if it is neutral charge, what we see, when dielectric constant is increasing of the biomolecule, then sensitivity, current sensitivity is increasing. Similarly, ion by I of ratio, pink color, it is increasing with the increasing dielectric constant, and threshold voltage sensitivity is also increasing. Now coming to negatively charged. So with the dielectric constant, it is increasing, but with the if we see the concentration, this is basically concentration of biomolecule, charge of the biomolecule. So if negative concentration is increasing, then in that case, when 3 to 5, 7, 9, it is increasing, then in that case, sensitivity is decreasing. And when we come to positively charged biomolecule, then with dielectric constant also, sensitivity is increasing, and with concentration of biomolecule, sensitivity is also increasing. So these are the effect. This way our biosensor will be working. It is going to detect some biomolecule. So these are some application. Maybe low power. Low power means when small, this leakage current is very small, so tunnel field effect transistor off current is very small. In the previous device also we have seen how to reduce the leakage current. And in biomedical, like to detect some biomolecule, how we can use these devices as a biosensor. So this is from my side. So session, if some queries are there, we can see.
Any queries?
Any queries? So I'm giving my email ID also. If in future also some thing is there, some query, something, you can mail me. I'll try to reply.
Thank you very much, madam, for your insightful and thought-provoking session. Your ideas and expertise have given us valuable takeaways, and I'm sure participants will benefit greatly from this knowledge in their academic and research pursuits. Thank you, ma'am.
Thank you. Thank you. So shall I leave now?
Yes, ma'am. Thank you.
Oh, okay, thank you.
Now we move to our second session of the day. It gives me immense pleasure to welcome our next resource person, Dr. Shanmugakumar Murugesan sir. Dr. Shanmugakumar Murugesan sir is an academic and deep tech entrepreneur with a PhD in computer science and engineering from IIITDM Kanchipuram. With over 14 years of teaching and research experience, he has worked extensively in VLSI design, embedded systems, and product innovation. He is the founder and CEO of Seven Horse Agritech Private Limited, where he leads cutting edge hardware and AI solutions for agriculture. His journey bridges advanced design research with real world impact, inspiring students to explore innovation driven careers. With great respect, I invite Dr. Shanmuga Kumar Murugesan sir to take over the session.
Hi, ma'am.
Hi, sir. Thank you,
So,
sir.
yeah, good
Uh,
evening.
Good evening. Yes,
So,
sir. You can take over the session now.
sure, ma'am. Yeah, thank you. Hi, all. Good evening. Okay, so we'll do a small activity and then we'll jump into our discussion, right? So, okay, whoever listening me, can you please raise your hands? Just raise your hands. Nothing else you need to do. Whoever listening me right now, raise your hands. Okay. Okay, so around 10, right? Okay, so good. Out of 110 is 10. Good. So I'll be very we'll have very generic discussion. I'll not go more deeper into any more technical discussion. Okay, let's do something what exactly we need. Okay, so that's what I want to take it. So I try to wrap it up a bit early, right? So if you guys are with me, yes, good, then we'll start. Okay, so I just want to confirm, is there people who are actually listening me? So great, thank you so much. See, of course, I know, right? So evening in home will be really difficult, but yeah, thank you so much for being here, and I'm really happy to pass whatever that I have learned. I'll pass to the faculty. Faculty will take this to another thousands of people, right? So around 110 people, then it'll be really a great, I would say, a reach, right? So I will have some questions. Okay, maybe you can just type in your chat so that I'll also feel more interactive to push more information. Okay, that's one request I put to you. Okay, so with that, yeah, I will jump in. So today, what we are going to discuss is we're going to discuss about how this AI is actually doing, I would say, revolution. Okay, so generally we call revolution means like into 10 times, right? So 10 times scale that if I can able to achieve, then that is called revolution, right? So I think the AI on the chip design, especially on the verification and the other sides, it's really doing a great job. It's doing actually a revolution. Okay, so how it is doing it? So, and I just want to understand how good you guys actually using AI tools like ChatGPT or Gemini in more deeper, or any other small tricks to use it more effectively, right? So this kinds of discussion also I'll be trying to take it, and I'll cover it up, right? So how this VLSI, especially on the design part, how great this AI is involving, right? So and then like we'll discuss about AI agent, right? So what is AI agent, and then of course if you have heard about it, if it is not, you should really go and read about what is agentic AI. It's like it's really crazy that it's changing the world. So I think especially maybe if you guys are doing research right now, or like maybe you are PhD students, this kinds of tools that what I'm going to share, I'll share like no small walkthrough to that, like Google Notebook LM specifically, I would say. So I think that will be really helpful for you also. So maybe if you are doing research, or even you are in your personal day life, you can use the tools, right? So that's how it's the beautiful AI become, and anyone can able to use it just to interact that with your native language, right? So preferably English for us. They have no other option. So it'll be a really good session. I'll take it very short. I don't take it more like no. I don't take it till 9 o'clock. I'll try to short it a bit early. So if you are with me, then we are jumping in. Okay. So I'm sharing my screen. Yeah. Can you see my screen? Anyone? Can you please confirm?
Yes, sir, but it is little blurred, sir.
How about now? Can someone confirm, please?
Sir, it is visible, but it is little blurred, sir.
Okay.
For me, it is okay, sir.
Okay, ma'am. Great then. Thank you. Okay, fine. So what the title that I have given for the today discussion is like from code to silicon, right? So AI powered revolution in RTL design workflows. So it's simple, right? So what is RTL? So you got an idea. Your idea, you just need to convert that into an algo, and then you convert that into an architecture, and then you convert that into a code, maybe preferably Verilog, VHDL, or SystemLog, whatever you take any SDL codes. And then you're going to put it on FPGA, preferably if you're trying to prototyping it, or and then you convert that into layout, and then you'll go for fabrication, right? So that's very simple, high level discussion if I want to take it. So simple. I got an idea to make a chip, so I'll just like try to make uh, basic architecture, and then like proper algorithm, maybe how does it completely works, the full workflow, and then I'll make deep architecture with gate level, and then I'll convert that into a code, the HDL code, and then I'll convert that into layout. The layout I'll give it to Foundry. Foundry will gives me a chip, right? So that's a simple process. So, but it takes a lot of time, of course. But I would say like it's an eagle view of what this VLSI is, right? So very generally. So in this, we're going to discuss only about start from the idea to get the code, right? So that's exactly the RTL. I mean to get the code and do the verification. Okay, so let's try to understand very surface level stuffs on that, right? Okay, that's our overall discussion. So we're gonna dig more deeper about how this AI is revolutionizing the chip design, right? So okay, I just want to add one short story to you, right? So in this, whenever I see this AI is helping chip design, and then chip design will help back this AI. Okay, so simple. So everyone does simulation, right? Of course, everyone is professor here, all are doctors. So everyone did a simulation. So you know the power of simulation, right? So in US, NASA, when they launch a satellite is supposed to go and reach exactly to an orbit. So orbit is depends on weight of the satellite and the distance between the Earth to that specific orbit and the rotation speed. Right? So this exactly the calculation. So you get only 5 to 6 meter of window where you have to place your satellite. So building a satellite is easier, but keeping the satellite in that orbit is the most difficult job. So NASA was doing somewhere around like before one launch, they tried 200 times of in a test bed. They tried 200 times to find out the optimal fuel to fill the rocket. Okay, so this was a story till 1980, 1985. So the moment they got a computer, the moment they got an IC, the moment they start doing the calculation, they started doing all this calculation on a computer. Computer is faster calculation. And they started building a beautiful interfaces where they started giving a lot of input data, right? So that's exactly one of the very deep birth of chip design also, I would say. Okay, so they started doing more calculation. This 200 times of testing on ground, which means that look at their wastage, fuel, time, everything is wasted, right? So now they test only 16 times because almost in the simulation, in the calculation, they got an optimal numbers. They started filling that. You understood, right? So that's it's a high tech science level, no? So they got it. So now 200 kind like simulations, sorry, 200 experiments to find out the optimal fuel. Now with the help of simulation, it has become only 15 to 16. Can you see the drastic change? And look at the beauty here. Okay, this is not the beauty. So this is the beauty of simulation. Okay, now the chip design, it happens in 1970s, 1980s, right? So the simulation got birth after the chip design. Now eventually what happened, the chip design was like one separate sector. They started doing this chip design as a simulation. So by doing this more simulation, I achieve better results in faster way because we save a lot of time and cost. Correct? No, that's the beauty of a simulation. Now what happened? We keep on doing simulations so that we got optimal chips. Now optimal chips become more powerful, which means that this is more calculations. I started doing simulation more faster and better, and this start helping me to build even more better chip. And can you see the loop? And we call this as a virtue loop, right? So it's virtue cycle, the actual word is. So means like it's both is helping each other to grow faster. Now the same pattern I'm seeing in AI with chip design. Now exactly where the AI is running on the chip designs. Now in the chip, right? Ultimately, NVIDIA, their GPUs are the one who's like completely powering all the AI models, correct? So it's basically a chip. Now with the help of AI, you start making better chips. So better chips will give you better AI. So better AI will give you better chip again, right? So can you see this one more virtual cycle here? Okay, so that's what I see. Okay, so it's my thought, and I see certain things happens in the real world in the same aspect. Okay, so I mean this is the most powerful way that you can able to learn things faster and do things faster with help of AI, right? So maybe majority of people would have used your chat GPT or Gemini, right? Okay, so before I jump into it, okay, I have a very short question. So if you can give an answer, I'll be very, very happy. Okay, just typing a number or say yes or no. Okay, so how many of you use ChatGPT or Gemini or any AI tools, LLMs? You can raise your hands. Okay, I'll give you really a good secret. Okay, so it will really enhance your, I would say, maybe your productivity, right? So simple hacks, right? So can you please raise your hands? Okay, yeah, one change is there. Great. Okay, see, I think I strongly believe almost 90% people for sure will be using any of these AI tools, right? So let's take an example. How many of you type, okay, more than 20 words to ask a question to ChatGPT? Okay, you can just type yes, yes. Okay, above 20 words, yes, one. Okay, above 50 words, I'll write like whole story. This is what I want. Okay, and in fact, 50 words you can write the whole story. So if you look at, okay, so I have seen a common pattern with a lot of people, right? So they just go and write a very basic question to a ChatGPT or Gemini, any LLM model, and it give you an answer. Okay, what you actually should do is you should really understand what is the AI. Okay, what is that exactly AI? Okay, so simple. What is this exactly LLM? The large language models, that what you are actually speaking. So LLMs are very simple. They have trained with lot of text contents and lot of language with sentiments, with of course not emotions, okay, with a lot of sentiments, right? So with a lot of grammatical, with technical, with understanding in every aspect, they have built the model. You got the point, right? Yes, sir, exactly. Yeah, prompting is important, more specific, exactly. So if you look at, if you try to understand this AI, it knows almost everything in this world. You understood, right? Okay, at least to a certain extent, to whatever that we are thinking on our level. Okay, so it's almost has like the overall knowledge of everything in this world. So let's say you are a very great genius in the world. Okay, I come to you, I ask you a question, sir. I just want to understand about rain. Okay, what do you give answer to me? So you are a deep researcher. You know all the deep more research about everything in this world. Okay, I come and ask you a very generic question. Okay, I just want to understand what is rain. So when the genius fellow, he had a lot of options to share to you. Okay, so and it picks very easy way so that I'll try to understand, because your question is very basic. Its answer will also be very basic, simple. Okay, very very simple. So what exactly that AI does for you, whenever you ask very simple, not more generic, and it gives you more generic answer. Okay, so what exactly you should do is you should follow certain rules. Okay, so I am going to tell you a small mantra. Okay, just like try to remember it. I'm just typing in the chat. Okay, so first what you should do is you should define what. Okay, sorry, first you should define a role. Okay, for example, right? So let's take a small example with our own course and what we are doing right now, right? Your FTP. You take an a one new chat. in any of your LLMs, whatever that you use, first you start telling it, okay, you are an RTL designer. You are going to help me to build a beautiful architecture for so and so specific purpose. Let's say I'm going to build a Mac multiplication accumulation unit. I just want to build it. So I just want to make this as a GPU model so that I want to run a small AI inference on top of this. Simple, okay? So this is the whole objective that you want to build it. So how you define this to your LLMs? First you say you are an RTL designer. And then this is the role, okay? And then what you should do is you should define task, okay? So what it's going to do, okay? You are going to help me to build an architecture code, means an Verilog code to do this specific function, which consider all the input outputs and your pipelining or whatever the things that you can actually define in your English. That's what I exactly mean. Okay, so you define this as a task. So first, any research or any important thing that you deal with your AI models, with your LLMs, first you define the role. Okay, then you define the task. Okay, then you define the context. In what context? Okay, I am building this for a power optimization. I'm building this for an area optimization. Okay, I just want to run almost like 1024 into 1024 matrix multiplication. I just want to perform at 1 clock in a whole parallel system. My input line should be like this. Everything we can able to define. Simple. Or let's say you do a research on your PhD or in any specific topic, you can follow the same principle. Okay. Okay. Sorry about that. The kids are at the home. Okay. So then you have to, okay. In fact, you can able to use this for any of your research. In fact, let's say you are planning for a tour. Okay, you can say you are a tour resident. You are going for this place. I just want to do a very optimal cost trip. So search in the web and then give me all the possible hotels on the itineraries. So literally, you can actually do anything. Okay, so that's why they call it as that's why they call it as intelligent, right? So the intelligent people does it. So whenever you speak with your AI, so please do remember this role, task, context, and what you should define is you should give reference. Okay, so you give a reference. I just want a result in the form of table, or okay, follow this PDF as a reference and give me a report like this, right? So you can able to refer to something. Okay, you can refer. Okay, by referring this, can you give me a result in this form, right? So you can basically get more confined results so that you can save a lot of your time, right? Next is your evaluate. Evaluate your result. If you are not happy, you go for iterate. Simple. Okay. So this is, you maybe those who are listening, you should really follow this whenever you use your AI and look at the quality of the result that what you get. Okay. So I very strongly insist you to please follow this when you do research or when you do any deeper technical discussion. It's gonna help you. In fact, it helps in every case. Okay. So good. Now let's jump into the topic. So do remember role, task, context, reference, evaluate, iterate. Okay. So really thoughtfully create really excellent input. Okay. Maybe something you can able to keep an acronym so that you don't forget it. Okay. So keep this as a sure mantra. And I damn sure I'll bet you this is gonna make you crazy when you work with proper LLM with proper prompting. Okay. So that's what one of our professor have kept in a text, right? So it's all about prompting. Simple. You are going to speak with another person who knows almost everything in the world. So you have to put a question more specific so that you get a specific answer. If you put a very generic question, what you get is a generic answer. Simple. Okay. So good. So now we're gonna jump into our topic. Okay, I just try to be a bit faster. So Moore's law. So we know Moore's law, right? So who's Moore? Jordan Moore, and founder of Intel. So he gave a challenge to his employees. Says like, can you guys make double the chip speed? Okay, so reduce the power by root 2 times and decrease the area in 18 months, like by half. So this was a challenge he gave to his employees to achieve, and eventually that has become a law. So we have been followed for so long time, and eventually now this become a problem because of we started doing billions of transistors in the one small chip. So now there's a more possibilities. There's a more chance of an error. There's a more chances of making it hardware possible. Okay, so what do you mean by hardware possible, right? So doing design, everything is simulation. Okay, at the end you want to make that into a physical chip. No, have you ever imagined how does these people make this chip in nanometer? How does people make this in, I mean, nanometer is like something even the smaller the size of our red blood cell. Okay, in your body there's a RBC. What we are telling is less than this size of RBC. Maybe it's your RBC is somewhere around 40, 50 times bigger than your one transistor size. Okay, that's the level that we are actually fabricating it. Okay, how it's all possible? Now we are at 3 to 4 nanometer. Beyond this, it's really difficult. Okay, so now, but the A is gonna assist to break this barrier. Okay, so that's what I really believe it. Okay, so why this Moore's law is a problem? Because of the silicon wall. Why the atomic size? Point number one. And two, we reached almost size of an electron. So now what you do with switching? Okay, maybe the best you can able to reach is one electron, one transistor. Okay, this was a proposal long back. Okay, so maybe that's possible. Okay, that's a really great crisis. Okay, so I just classified this whole session into 5 sections. Okay, so we start with this. So crisis in the chip design. So what is PPA wall? So in the whole technical world, okay, so they all speak about PPA, performance, power, and area. So we, as a VLSI guys, we know it. We cannot achieve all the three at the same time. Correct? Improving one often hurts another, which means that if I focus on power, okay, I should actually reduce my performance. Or if I focus on my performance, I will increase my power and I will increase my area. So there is no a possible way where you can able to achieve all the three at the same time. But this is becoming possible now. Okay. So that's a comparison I just want to make you. Okay. So achieving all the three at the same time was literally impossible for so far. Okay. What with human beings, that what we have did so far, like amazing. I mean the real volume. Okay, so but now this is becoming possible. Okay, and the other bigger problem in this is the verification productivity gap. Simple. Okay, so maybe many of you guys are from digital design, means like sorry, testing. We'll say system testing, digital testing. You don't know the complexity of the testing of a chip, right? So I just like want to put a small comparison. So let's say you are buying a three different type of computer. Okay, the computer one is your let's say a small desktop in your office for your personal usage. The computer 2 is a workstation where you run all your research and codes and the basic stuff, and you are buying another bigger server where the server is going to help you to do huge computation. Okay, let's say all these three are building with the same processor. Let's say all these three comes with the same powerful processor. Let's say the processor is Threadripper, or let's say our Core i9 from Intel. Do you think all the three, I mean, it has been fabricated from the same wafer? Okay, it has been fabricated from the same layouts. And do you think the cost is the same? No. The processor for the workstation is actually, okay, the processor for your desktop is actually cheaper. It's the same processor. Number of cores is same, speed is same, everything is same. Your desktop processor is cheaper, your workstation processor is a bit costly, and your server processor is very costly. Why? Because this has undergone for an intense testing, right? So before, okay, that's I'm speaking about the post-production testing. Now we are speaking about before production. Okay, so the verification, what are the design that you have made, how to verify. The problem with the verification, the problem with your testing, almost both are same in certain cases in terms of your test benches. your possibility of verification is like super exponential. Let's say you want to test all the possible cases of your microprocessor, means the processor in your laptop or in your phone. Let's say you started testing today. Your grandchild will come and check the result. You understood, right? Let's say you want to check all the possibilities. Only your grandchild will say, yes, grandfather, the chip was tested, it is success. Okay, you cannot see it. And that's a real fact. So the verification was one of the bigger challenge. This AI has completely broke it. Okay, so verification was not the challenge. Just a small number, what happens in the real world. Okay, especially in the industry. Let's take a project. Okay, only all other design tasks start from idea to your RTL to pipelining to your all your latching to your IO inputs, like everything takes only 40% of the time. Verification alone takes 60% of the time. You understood that how complex this verification has become. You got it right, because the possibility of testing and to verify this is very high. Okay, as I said, it's so many possibilities. You are picking best cases and you are trying to justify it. Okay, the solution to this whole complete problem is, in this industry we call this as a shift left, which embeds intelligence at the very beginning of the design process. Start from your ideation, you follow this whole structure. Okay, shift left towards, start from every layer. Okay, but if you go and ask your AI, okay, to, let's say you go to your LLM of your ChatGPT or someone, and you ask it, okay, I'm just trying to build this. Can you design, verify, and optimize, and then again you would verify, and then give me a best RTL design so that it'll go for fabrication. If you ask with your ChatGPT, you will not get the answer, and it cannot do. Simply, if I ask me, ChatGPT cannot do this job. Why it cannot do this job? Because it's a large language model. It is meant for another purpose. Okay, so now for our specific cases, there should be an agent. Okay, so that's what exactly it has becoming. Okay, LLM is very, it's good at very generic. Okay, certain level of research with conversational, it's all really good. Okay, the moment you go more deeper, the moment you think so longer, that's where it miss its concept, it misses context, it misses its references, it start mesmerizing. We call this as an hallucination. That is a typical problem. So LLMs in chip design has a lot of challenges, but in your live design, it has a lot of advantages. Okay, as I said earlier, you use it like, you can plan it. If you have any specific doubt, define it. Okay, it gives you a very clear answer, right? So be more diplomatic. Okay, so just give a try. I mean, okay, so, and there's a misinterpretation. Okay, why? Because when you start building a system, it takes months to do the whole job. Okay, and the size of the whole model become exceeded to understand, and they start hallucinating. Okay, so that's exactly the misinterpretation. So this is a typical problem with this LLM. Okay, the solution for this, if you guys really want to work on this aspect of agentic workflow for this VLSI, that's another crazy other new research area. You can think of it. Okay, so now, because like VLSI has a lot of process, you understood, right? So it's like a lot of one small segment. Okay, so simple. Okay, for your understanding how an agent work. Agents are the fellows who work for you. So first your job is prompt. Simple, as I said, prompting. Follow this role, task, context, reference, execute, and then iterate. Okay, go to a chat GPT, give your idea, ask this fellow to refine your prompt. Okay, you get a beautiful prompt. Come, put it in your LL, like, ask this fellow to generate an code for this. Before that, you have to define your RTL designer. Okay, you want to do this work. Okay, specific, be more specific towards the power optimization. I'm not worrying about my delay, or I'm not worrying about my area. You can say all this normal way discussion. Okay, and then you say, I am building this macro unit of let's say 1024 to 1024. So give me with all the possible inputs, outputs, and then pipeline stages, what order, this order with this delay, or like everything you can specify, and then you will get okay, and then you pass this prompt to your RTL generator. So that's another LLM. Okay, where you have given your information about your Verilog, you have uploaded your Verilog book, or you have uploaded the syntax of your all the Verilogs, let's say in a case if you wanted it. Okay, or just like in a specific you say prompt, okay, I am looking for a Verilog expert, okay, start helping me and then Verilog aspect, okay. You can put it in this way. So, and then like, you will get an RTL code, okay. And then there's just tools from your Cadence, Synapses, okay, Siemens or Mentor Graphics or from Xilinx, okay. Every fellows now they have an tools. With I don't know how many of you guys are exploring. If I strongly recommend you to go and explore the tools because it's going to save you a lot of time, okay. And the tool like lint agent, okay, so where a static tool checks the codes for errors with all the possibilities, okay. Then when the code was completely fine, then by giving this code with all your specific cases, you want to create a test bench. Generally what we create, right, that's a code that should do create a test bench for this code where you get a lot of possible inputs with the golden response, and then do give this to a simulator, and it runs test and check the functionalities with your test bench, and it all goes in hand and one by one, okay. Then once you get this whole simulator agent completed, then go look back your results, evaluate, iterate. You understood? So it's not just one tool, it's gonna give you the whole magic of everything, okay. We are not in that AJ world, maybe wait for another 3-4 years, there's the chances, okay. But still you have to specify, okay. So maybe I'm really a good I would say great inspiring fellow of AI whatever happening today, because it's changing the world completely, there is no doubt in it, okay. And no one can able to deny. And what will happen to the future, okay, so we hope for the best, we do all the regulations, privacies and things are happening, but still there is always a chance, because there's a digital world, there's a problem of your data and your privacy, okay. But still, okay, so somewhere in the terms of growth, in terms of optimization, it's really doing a great job, okay. So that's the beauty of AI, and basically this AI based agent workflows, they are rock stars. You should really start using this in your research if you really wish, and you will see your result and you see your optimization, it will be really crazy, okay. And you can build it for this, maybe if you want, for your specific cases, if you want to build this, I recommend you to go with either Na10 or GenKit, Google GenKit, okay. GenKit is like easily you write a prompt and then you build an agent, you connect your Gemini, all easy places, okay. Go to YouTube, there are a lot of videos, they will explain you step by step how to use this, okay. Then upon your use case you start building it, okay. So now how this fellow means this AI which is solving the PTA puzzle, and how this has actually happens, okay, simple. I just give you my own example, okay. When I was doing my PhD, okay, my PhD is all about making a network system, okay. Means like I made a processor, network processor, we call that as an NPU, network processing unit, where it receives packet, it processes the packet, it assigns the co-processor to do the jobs and so on, okay. So my whole job was to build this network processor and the co-processor. That was my PhD. So I was trying to build an 32-bit processor with size of 104 specific information from the packet to process it. I was trying to replicate this for at least like 1 million rule sets, because that's what typically the server and the high level routers will deal with, okay. So I made an architecture, so it was working. I'm speaking about 2014, 15, 16, okay. I'm speaking about that time. So of course not now. So my code was somewhere around like 3.7 lakh lines altogether, all as completely Varila code, half structural, half behavioral, and then some are data flow models. Okay, it's just a mix of all three together. And I was trying to run this on a simulation. Okay, I run simulation. I wait for 3 to 3.5, 4 days, because even though I run in a bigger computer. Okay, so my CPU that was costing somewhere like 15 lakh rupees at the time, even though I'll be waiting 3 to 3.5 days to get one the actual test output. Okay, so what I do again, I look at a lot of errors. I'll start sitting and then I'll be keep tracking what exactly happened, which line or which way, where architecture I have misconnected, or like where I have misinterpreted or miscalled this specific variable over there, I'll be keep checking for another 1 week. Okay, so after 1 week again I start running it. I'll be keep waiting for another 3 to 4 days. After 4 days I'll get another result. I'll be keep looking at to find a bug. I'll fix the bug. I'll start running it. Okay, they can bug fix it, take another 3 4 days. Again I'll start running it. I'll wait another 3 4 days. Like this I have run for my life for another almost 1 year. Okay, so this is typical example of optimizing your code, specifically debugging your code when you write a lakhs and lakhs of lines of codes. Okay, and this is my own experience. Okay, and I have seen a lot of my colleagues, my peers, like if everyone does, even in industry people does that. Okay, but they have higher the computation, but they have higher the complex in the design also. Okay, and it's a typical job of uh, designer. Okay, so that's the typical job of designer so far in the world. Okay, now today what happened? Okay, AI autonomously explores millions of design options, where for me in my case I took years. This fellow does all the job in minutes, seconds and minutes, not even hours, I would say. Can you see the difference, right? So the way how fast you can able to reach faster in your optimization, right? And overall, with the help of AI, with the agent, okay, overall industry standard, what they said is they have reduced, almost reached 20% optimization. Maybe you will think 20% is like, you said 10x in the growth and then 20% optimization, right? A world standard on PP optimization so far happened is 2%. 2%, okay? And here with AI, it has achieved 20%, okay? A staggering number, what they have achieved it, okay? And this is all about design, okay? Now let's jump into verification. As I said, verification is 60% time. And how this AI is helping this verification? AI transform this verification because, as I said, okay, my own experience of blind search. Now today what happened? It's look for a targeted specific cases where you say go and find exactly in which bit of output where there's a more common error, where I can able to go back, trace back. This is what I was doing physically by taking days and days. Okay, there are days will not even have a sleep because if I miss it, I'll miss the whole continuity. I'll be keep on working on that because there's a need for that at the time. Now the case has been different. Okay, steering test towards complex concern and the design where bugs hidden. I did this all in a very short time. Okay, in verification, the achievement with this AI, the achievement is 10x. That's the reason I put a word revolutionizing. Okay, so engineers new co-pilot. So argument, it's not a replacement. Okay, so never ever think AI can able to replace an engineer if you are not if you are highly skilled fellow. Okay, it can able to replace you if you are just an unskilled, like just one job that you are doing it. If you are creative, you are a survivor. Simple. If you are not creative, if you limited only with basic thoughts, there's a question mark. Simple answer I would say for maybe if you have a question, what happened to the future of AI? Okay. See, AI evolves. In fact, that's how every technology has came to the world so far. Okay, start from your steam engine, your electricity, your motor, your engine, your IC, and today the data, and now with huge amount of data, the AI, and they too again co-live each other. Okay, so because data is all trained with AI, right? So IoT is giving so much of data to it. That's industry 4.2. So specific tools maybe I want you to explore. So Synapses, the DSO.ai. Okay, so what is the number that I have shown you? 10x improvement, 20% achievement in PPA. As a standard is 2 to 3%. It's 20. It's an amazing number. And what they achieved is like 3x productivity and 10x faster coverage in terms of verification. In CAD and Cerebus, 10x productivity, 20% PPA improvement. Okay, look at everyone have given in percentage of in 2 digit, and world has never seen the 2 digit so far. Okay, so captured AI or like an Aspilia, and there are a lot of tools like this. Okay, and or you can build specific for you with more specifically by following one good chat by paying just like 400 or 2000 per month from Gemini or for Google AI workspace, sorry, just for Google AI Pro, or like pay some 400 rupees to a chat GPT where you get a project, you start building a project out of that. Okay, not just only a chat. OpenAI by paying 400 rupees per month, where you can able to build a project. Where in the project you can give all your books, like your Verilog book or any book or your research paper, and you can stick with only within that specific topics on the papers, and you can discuss it. Okay. So don't know what's exactly happening in AI. AI is becoming the compiler of the hardware, where you can able to do lot of plays and then you can reach optimized hardware faster. Now, if I look at another comparison, how this chip design and simulation was helping, today AI is helping the hardware to evolve faster. Okay, that's my actual comparison. So now an intelligent engineer will actually survive. The specific word I put intelligent because they should keep learn what how this AI is evolving faster. You also should evolve. Okay, freeing engineers to focus on high level architecture, think more of optimization, think more of new level of algorithms, new level of applications, and so on. Not by doing just the labor job of talk verification. It's like very difficult job. Maybe if you want to put one more real world data, so in India there's a huge amount of VLSI industry, but majority of them do only verification. Okay, it's an information for you. Okay, which means that we don't do design, but today and now the government is pushing like almost 10,000s of crores towards chip design, towards VLSI, towards architecture, and towards an application with specific architecture, right? So if you being a professors, like if you have an if you're interested, you should really explore with AI. How can you able to help this real the other side with industries? Yeah, that's a see. It's all about you need a patience to sit. You don't need to learn a very long. You don't need to learn any language. Okay, trust me honestly, you don't need to really learn any language because of course being after a certain age it's difficult to sit do basic coding, right? So now but you have a thought. Okay, with your experience you had a lot of thoughts. With that you actually can use it. Okay, simple. So skill domain is design. So digital skill set, what you need is very large HDL coding. No, today what you want? A natural language. Are you really logically enough, intelligently enough, reasoningly enough to write a clear cut prompt? First point. That's exactly the design today. Optimization, manual scripting, tweaking. Oh my God. Now define a reward functions, which means that you do optimize for this specific achieve one, then you go to the next state, give a reward for it. Okay, where just keep on define optimize. Okay, so you can stick with more pipelining stages or like no find an optimal pipelining stage what exactly works for you system and so on. I mean, okay, so verification, manual testing, that's another biggest challenge. Debugging is the A process, it has become super faster. Okay, so what I exactly mean is the path from code to silicon is being redrawn and A is holding the pen, which means that now there is a huge change is actually happening more towards AI with chip design because chip design was one of the complex thing. Okay, I have one short question. Okay, so yeah, with this my presentation I'm stopping it. Okay, so yes, sir. So Nagaraj sir has a question. So physical design also we can get prompt in Chat GPT, sir. Okay, you are asking a question to me. I believe. I think it's a bit difficult. Why? Because it's more of pictorial. I think you should check with the cadence in that cells. I think it is there to some extent, but I'm not really sure, sir. Okay, so please check with any tool vendors. I think they will tell, or please, maybe yeah, it's a good way to like explore it. That's a great, right? Okay, so good. So now this is what exactly the AI and what how this AI is actually revolutioning this specific way, let's say, because the group here is like very unique, you know. We are very more confined only to the specific topic of VLSI within this that we cover, right? So it's like that's why I'm more specific towards it, right? Okay, so I have one more question. So maybe if you give me hands up. I'm very happy so that I'm not speaking with wall. I speak with people. I will believe it. Okay. So how many of you are aware of Notebook LM? There is an Google app called Notebook LM. How many of you are using it? Can you please raise your hands? I hope I'm not speaking alone. Yeah, great. Thank you. Uh-huh. Notebook LM. Okay. So it's a magic tool. Okay. Oh yeah, it's a magic. I'll show you a short demo of Notebook LM. Okay. So I think this will be my paid version. So, okay. Simple. Go to Google and type Notebook LM. Just click Notebook LM. Log in with your Gmail. Okay. Don't do anything. Just log in with your Gmail. You will get a new window like this. Okay. I just opened a very free one. Okay. My other account has premium, so it will show a lot of other features. So maybe I just want you to try this first. Okay. So go open Notebook LM. Log in with your Google. Simple. Just your Google account. Simple. Go click Notebook LM. So create new notebook. So you will get a Notebook LM, add source. Okay. So this Notebook LM is a tool. Okay. What exactly it does is it's going to build a notebook for you. Okay. For the specific documents that you are uploading it. Okay. The document that you can able to give to this specific project in this one Notebook LM, you can able to add a source, choose a file. You can add PDF. Okay. You can add PDFs. You can add PDFs. You can add PDFs. 1, 2. This is PDF. Okay. 2. You can straight away click Google Doc. It will open your Google Docs. Any report that you want to import, you can import it. Simple. Just pick, click, import. Done. Google Slides, if you have, you can click it inside. Your class, your feedbacks, anything that you can able to do. Okay. If you have a website, click add a website. Okay. If you have a YouTube, okay, let's say you have 10 YouTube videos which is discussing about, let's say, pipeline optimization. Let's say how to avoid an hazard, or let's say how to get away from the negative slack in your pipeline design. Okay. Let's say you got like 10 videos, like one small 10 research paper. Okay. You put all, you got it right. So YouTube, just paste your YouTube video link here, right? And okay, address was here, right? So YouTube link. Let's say you have a big copy text, copy paste, done, and they simple. You got it right. So you can import any of this type of documents into this. Okay. Or let's say you don't have any document. Okay. I just have only a thought. Let's see what's happened in this. Just click here. Okay. Just click here. Where it shows discover source.
Screen is,
Sir,
sir,
excuse
your
me, sir.
screen is not visible.
Screen is a bit blurred, sir.
Okay. What may be the reason? How about my voice?
Voice is fine, but the screen, we are not able to. Now it is becoming better.
Okay. Can you see the screen now?
Not clear, sir.
Okay. 1 minute. What I do, I'll stop sharing. I'll reshare. Can you see my screen now? Can you see my
Blurry,
screen?
sir.
Can you see my screen now?
Not clear, sir.
No, no, sir. Same,
It is
sir.
become further blurred.
Network issue for me. In fact, I changed to my phone. Can you see my screen now?
No, sir.
But now, can you see the screen now?
Sir, screen appears, but it is still blurred, sir.
I'm really wondering why it's blurred. Can am I a host for this meeting? I think what is the problem? I'm really wondering. I have changed my internet too, so internet is faster. So I get around like 80
Um,
megabits. Shall I exit and rejoin?
yes, sir.
Give me a minute,
Yes.
okay? Yeah,
Yes.
give me a minute. Can you please confirm? Am I visible in the screen?
No, sir. No.
Can you see my Chrome page?
Sir, we can see the page, but we can't read the text there, sir.
It's blurred, sir.
Okay, so anyhow, okay, simple, right? So what I'm going to tell now is I'm going to just simply tell you how to use this tool. Okay, a notebook LM, it's free for certain limit. Just go and give a try on this tool. Okay, so it's like go to notebook LM, just Google, log in. There'll be three sources. Okay, look at the left side. That's a source where I'm running my mouse, right? Sorry, mouse cursor point. Click add resource, you add any file. Let's say you have 10 research paper. Let's say you are you want to understand more deeper about the research paper. Let's say one specific question. Upload all the 10 research paper. Okay, start asking clear question. Do remember that specific task. Okay, over here you don't need to define a role. Yeah, maybe if you define email, it will be good. And do remember this notebook LM is not like your chat GPT or your Gemini, because chat GPT Gemini will do hallucination because it has lot of data. This notebook LM will limit only with the uploaded information that you have given. So what exactly that what we are trying to do here is we are actually trying to limit the whole knowledge base within this. The reference, anything that you ask a question, it gives answer with the reference. But this is not possible with your chat GPT or your Gemini. So come simple in the source add. In source, let's say let's say you want to give a give an idea. Okay, just give it. Okay, let's say I'm feeling curious. Okay, let's say it's come up with some random. In fact, you can define the whole story. Okay, because of the time limitation, as I said, like I'll leave you a bit early. I try to leave you a bit early. Okay, so let's say I'm curious, effect of quantum mechanics, observe effect, conscious, read it, function collapse, double digit. Like let's say if I import all this content, simple. Okay, I did nothing. Okay, I just go. I'm curious, so give me some content. It took a lot of content from this internet. Okay, so now once it is done, it's reading it. Okay, so the title it has given for this search is the enigmatic quantum observer. Something like more crazy thought it have come up with. The beauty here is, can you please look at here? Okay, now look at the left side is source, the mid part is the chat. Okay, let's say what, okay, look at it has recommended a question for you. what is fundamental nature of an observation and its impact on quantum system? Just by click. First, it gave a summary about the whole content. You have 10 sources added. From 10 sources, it gave content. Now you ask a question, it gives you an answer. In quantum mechanics, the fundamental nature of observation, and it start giving you an answer. Where you will see 1, 2, it's all your references that what it has taken from. It gives a very good answer. When you write your research paper, this will help you a lot. Okay, so keep the sack. It's free of cost and it's my gift for you. Okay, so now it's a beautiful part for your chart. Okay, now I'm going to tell you really crazy. Look at the third one, the studio. Okay, source chat studio. In the studio, if you look at, there's an audio overview. If you click this audio overview, it will generate a podcast mean it gives you 30, 27, 40 minutes. You can pick, customize. Okay, by clicking this edit you can actually customize it. So click, you customize short and large, default, எப்படி வேணும். Okay, how you want it, like brief, critic, debate, in what language you want this, English, Tamil, Telugu, Malayalam, any language you ask. Okay, look at Tamil, Telugu, Malayalam, every language, English, like check, let's say you want to understand Hebrew, any language, it will give you a podcast which gives a beautiful level of conversation. Give a try on this audio. Okay, 1, 2. Video overview. Let's say you want to go for discussion. Let's say you want to go for a class, you want to give a specific topic, or you want to make them small, kind of an audio video with the presentations. You can actually use this video overview just by clicking video overview. It starts generating. Can you see generate video overview, generate audio overview? This will take time. Okay, so don't worry, give some time and then come back and see. Third one is your mind map. Mind map is something very interesting. What it does, it gives the whole view. Okay, you give 10 documents. In this 10 document, what are things are there, how it has been organized, you can get the whole overview. Okay, and the reports, you can click this, it will generate a report in what way that you want a report. Okay, so you can actually define it. Okay, if you start paying money for this chat gpt, okay, so maybe you start getting, let's say if you go click project, okay, or like same, let's say I go for discover, I feel like same thing I'm doing it. Okay, I'm feeling curious, let's see what it's giving in my other account. But I strongly recommend go type. Okay, so tracing humanity struggling against infection disease and source immunity genetic adoptions. Okay, just import. Okay, can you look at my right side? Okay, left is like I just imported as usual the 10 pages. Yeah, you can actually add PDF and everything as I said just by adding it. Click. Okay, just upload basic interface. I think three journals they couldn't add in this. Okay, so humanity, agriculture, infection, disease, evolution. What's happening? Okay, it gave some gave some answer to it. Audio overview, video overview, mind map, reports, flashcards, quiz. Let's say you are going for an exam. You are keeping a small exam to your students. What you can do, let's say to specific one subject or one unit. Let's say you are teaching digital design. Let's say you are speaking specific about your what is called maybe your state machines. In the state machine you are speaking more specific towards one, upload certain documents or search on this some media, get some documents, create a questions. Okay, you have an option of creating more interesting questions with the flashcards and this quiz. Okay, and you can able to keep note, add reports, like so like, you can do a lot of things. Okay, and you can share with your friends the same project and you can share with your friends. Okay, so now this is exactly the notebook LM. Okay, it's one of the most powerful tool. Many people are not really aware, and I really, okay, look at the quantum measurements, the mind map. Okay, so what it discusses is the quantum measurement problem definition. It speaks about measurement of physics process. QM predicts probabilities, not definite outcomes. Incompatibility for 3 assertions, and you click, it expands, and the next is what is core concept in this measurement, right? So quantum state, entanglement, wave function collapse, observations. You clip only this quantum decoherence and then it gives a lot of topic. All these things has been discussed. So you get this entire structure of your whole course or this document, whatever have been added. This will help you, including even you write a code, let's say you can define this by clicking this, by clicking this. I will get this whole bigger view here. Okay, so it's like really bigger. You can build.
Hello, sir. Sorry
Yes,
for
sir.
disturb you.
Yes, sir.
Sir, the screen is so much blurring right now. Even not a
Okay.
single word is visible.
Okay. Um, okay. Fine. So simple. Okay. So what
You
I
can check
recommend is
check the chat box, sir.
yes. So I'm okay. I'm sharing the link of this notebook LM. notebooklm.google.com. Okay, just log in, upload your documents. In the left side you will see source. Okay, that's just three windows: source, chat, studio is where you will get all the summaries, videos, quiz, flashcards. And the mid one is what exactly will get it, the whole the chat, anything that when you write research paper, it will help you. And the left side is all your source, you keep add source into it. Okay, so that's exactly what I want to share. So if you have any questions, yes, we can jump. And I just want to add one more interesting thing to you, and I recommend you to go and read about one company. Okay, so where is it? Okay, yeah. Okay, so can you write a short? Okay, so which is the most powerful company in chip manufacturing, or in the industry of VLSI? The most powerful company in the world. What do you think? You can write in chat.
Micron. Micron.
Micron, Micron, interesting.
Yeah.
Okay, Intel,
And TSMC
TSMC. Wow, that's amazing. Okay, good, because they make
from
chips, right?
Taiwan.
Taiwan. Okay, great. Nvidia, of course. Nvidia is not okay.
NVIDIA,
Nvidia
yes,
is
from yes, yeah.
yes. Nvidia is the most powerful company because they make GPU plus software. In fact, they become powerful because of they make software also. Wow. So Rashid, Karadupullala Rashid, right? Yeah, Rashid. ASML. Wow, great. Okay. So there's a company called ASML. Okay, so what this ASML company does is something remarkable. If let's assume, okay, let's say there is a time machine for you. Okay, let's say you got a time machine, you travel back, you go and erase this company called ASML. Okay, let's say you got a chance. Okay, just in a hypothetical situation, you will not see this technological progress. Okay, so that's to be the honest. Okay, why? Because they are the one who make machine to fabricate the chip. Okay, that should be machine to fabricate the chip, right? That company is called ASML. Okay, so you should go and definitely go and look at this just their website. 2 3 more videos you will see in their website. Just look at that website. Okay, it'll be crazy. They are one, actually they are one of the technological pioneer. Okay, why I mean this point, because they were the only company in the world who can able to do this, the one and only company who can able to make this at 3 4 nanometer chips. None in this world can able to do. Chinese, Americans, none. These guys are from Netherlands. One company, okay, with very limited number of employees. All are super highly technically deeper knowledge people. Okay, so one of my friend even works there. Okay, we discussed a lot, and every research what they do is like mind blowing and the crazy researches, right? So it's like miracle what you see in their company. Just look at their website. Okay, maybe you will get that what exactly it is. Okay, so this is what I just want to share it. Okay, so now, as I said, how exactly this AI with agentic workflow typically we can able to solve it. So I strongly recommend you to use. There is na10.io. That's a website where you can able to build agent for you. Let's say you want to create a question paper, or let's say you want to evaluate an assignment that 60 people have submitted, you can build an agent for it. Okay, so just go to YouTube, try for like how to build a very small agent with Anyton or Lang or Jenkins. Okay, anything. Just give it a try, right? There are a lot of beautiful YouTube videos. Okay, so one of the most resourceful platform that it's always in your with your access is your YouTube. Maybe one recommendation I will give you when you start reading in YouTube is like you start paying premium to it, pay some 299 per month for this, so that you will not get advertisement, so that you will not get distraction. Okay, that's one recommendation I would say. And you in this today's world, in the AI era, being a deep researcher like you guys doing a lot of power optimization, low power design, pipelining, architecture, device level, any aspect that what you work on this VLSI. Okay, learn what exactly the AI tools are coming in that specific segment. Okay, like as I said, for PPA improvement, bbc.io in from your Cadence, from your Siemens or from Metagraphics or from your any company, right? So keep explore on this and then use your AI tools more productively. And I would say like it will be really great help for you. Okay. So with this thought, I'm finishing my presentation. Okay. So now if you have any questions, we can go for it or we can wind it up. Yes, if you have any questions, yes, please, you can open up your mic and you can ask.
Any questions?
Okay, so good, great. So I'm very happy to
Sir,
be.
thank you, sir.
Yes, ma'am. Yeah, ma'am.
Yeah, thank
Please.
you so much, sir, for your informative and insightful session. I think we have gained immense knowledge from your expertise, and it will certainly help in our academic and research endeavors, sir. Thank you so much.
Ma'am. Okay. So good. So I'm very happy. It's my pleasure to be here, where I had the chance to speak with 113 people. Okay. So at least what are the information that I try to pass, you pass to your students so that they'll get more, I would say like more deeper understanding. Let them explore more changes that what's exactly happening. As I said, simply today in this world, learn how to logically convey your things in the English form. That's more than enough. Okay, use your AI tools productively. Okay, so use it more wisely, and don't think of or some money to AI tools, because by paying it, it gives a lot of difference in the result when you use like basic. Okay, so of course money, anything comes with a cost. For them also it's a cost, right? So don't think of spending money for that. Let's say if you really work more. Okay, so it's all about your interest only. So great, it's my pleasure to be here, and thank you so much, and I wish you all the best. So here I'm sharing my email ID, shanmukumar@matic.1. So I'll be love to hear from you. Right. So great. I wish you all the best. I am happy that I'm part of this FDP program, and I thank Shruti ma'am and our HOD sir for giving an invite. And thank you so much.
Thank you, sir.
And if you
Thank
have
you.
any queries, please let me write to my email. Thank you. Bye bye.
So, as we conclude day 4 of our FDP, I sincerely thank all the speakers and participants for making it successful. Tomorrow we'll be stepping into the day 5 with even more exciting sessions lined up. So, dear participants, please submit your feedback, and the link is in chat box as well as in WhatsApp group. Until then, please stay safe, stay curious, and keep learning. Good night.